So our second speaker for today is Yakov Varshavsky from the Hebrew University of Jerusalem. He will talk about from character sheaves to characters of Deligne-Lusztig representations via categorical traces.
Okay, so thank you very much for the invitation and happy birthday to Joseph, which was already passed. Okay, so this is everything joined with, yes, I don't know whether it's called in progress or, so let's say, I hope it will be finished eventually. Gaitsgory and Rozenblyum. Okay, first of all, plan. First one will be some warm-up. I will talk about something that most people know, or maybe everybody knows, Harishchandra induction. Second, I will formulate our main result. Third, I don't know, depending on the time, I will talk about categorical traces. Categorical traces. Categorical traces. And after that, I will say about main construction. Plus maybe some remarks on the proof or sketch of the proof. Okay, good. Let's start. The setup is very, very elementary. I don't know, somehow. We will not go to too complicated Lie superalgebras. We'll skip to finite groups. So let G be whatever connected reductive group of a finite field. And then, let M BG be Levy. To those who forgot what is Levy, for example, you can take Levy. M is the centralizer of S, where S and G split those. Everything over FQ. Okay. Then for every P, every parabolic, we have for every parabolic P in G, which contains M, such that M is P modulo the unipotent radical. I believe it was Harishchandra who defined induction, which is from the representations of M of Q to over C or something. Actually, it doesn't matter. C, which maybe later will be Q bar. So first we'll go to representation of P of Q, which is just inflation, right? Because M is a quotient. So the diagram you have keep in mind is this one. So we start from here. You pull it back, consider the representation of P, and after that you take induction. Okay, so this is just usual induction, right? So this, and actually I will need, so I don't need it now, but alternatively, so every functor like this is given by bimodal. So what I want we want to consider the set over G of F of Q divided by the unipotent radical of this guy. So consider this quotient. On this quotient, of course, there is an action of two groups. So here there is an action of G of Q from the left, if you wish. Here there is an action of F M of Q from the right. Agree? So if you consider the space of functions, you know what? Let me just, I will. So at the moment it doesn't matter somehow, but later we will do Q bar will be important. So let us put it here it doesn't matter. G of FQ divided by this guy. So it's a V. So this guy is what? Of course, on this vector space there is a action, commuting action of these guys. So it is G of FQ, M of FQ bimodal. And then Harishchandra. What is Harishchandra? Let me not write all the indices if you don't mind. V, it's just, you take the following thing, you take just V, sorry, no, it's not good. Let me call it, let's call it B as B model, and V as a representation, and then it will be B tensor V over M of FQ, right? Of course, in this setting I don't need it, but somehow later we will go into generalize it, where this the way of constructing the functions will be to construct bimodal. It will be the only way possible. Okay, so yes, there are two facts. Let me formulate first fact one. Fact one, that this Harishchandra MPG is independent of P. So you need it in order to define it, but actually it doesn't important. If you take another one, another parabolic, it will be independent. And so this is the first part. Okay, maybe it's one. Let us say two. If you wish, Harishchandra functor is exact. In particular, it gives us, you consider it gives a linear map from the class functions. M, sorry. Of the class functions to the correspondent class functions. Given by, if you wish, its character of V goes to character of Harishchandra of V. Okay? And then fact 2 says that actually this map.
So fact 2 should be obvious, right?
Yes.
Semi-simple categories.
Yes, it's semi-simple categories.
Fact 1 is not obvious.
One is also very, very easy. It's just, you should calculate the trace, Marquis theorem for finite groups. So it is. I don't know. It's not obvious, but easy. I don't know. The question is obvious. It depends on the person. For you, it's obvious.
But there could be two parabolics which are not conjugate.
Yes.
It is still.
It is still true. Yes, it's still true, but it's easy fact somehow. If you just write down Marquis theorem, somehow you want to show, then this works.
But it will cause some simplicity.
Yes. Yes. You're right. You're right. It's because of semi-simplicity. Because later we'll formulate the correspondent geometric assertion, which will be okay. Yes and no, because it's true in bigger generality. Yeah, but you're right.
It's not true for P&D groups.
What?
It's not true for P&D groups.
It's okay. It's not true. Okay, it's not true on the level of representation. It's not true for Wikipedia groups. It's still true on the level of characters. You're right. At least if you do it correctly. Let's ignore it. Yes. Anyway, we are in the finite group. You are absolutely right. You have to be sometimes careful. Yes, but the assertion is it comes from geometry. And let me say what do I mean by this more precisely. We consider the following diagram. We consider M divided by somehow M. This is We consider it's somehow all the quotients will be stacks, and I don't want, I don't know. Some people write parentheses, I probably, okay. Anyway. So we consider G mod add G. We have this some maps, I don't know, alpha beta, just in order to not, yes. And then of course there is another induction. What you can do, you can consider the, what I will say, Grothendieck-Springer func. It will be from sheaves. In a second I will say what do I mean by sheaves. What you can do, you can map it from here to sheaves G adjoin G, and what it is. And you want, here you put beta shriek apple star. You can ask whether I could put something else. It actually does not matter, because this map is actually smooth of relative dimension 0. In particular, star shriek is the same. And this is map is proper, in particular push forward with star and shriek same. And the only thing, yes, what maybe I want to say, what is the sheaves? Sheaves meaning for every whatever stack algebra whatever x. When I say sheaves, I'm using notation of Dennis. Sheaves, it's the derived category, whatever, or infinity derived category of the yes, whatever, x in Q bar.
If it's smooth relative dimension 0, it's just a tag, yes?
No.
What is smooth relative dimension 0?
No, it stacks. It stacks. No, like for example, there is this vague example. Take x divided by not x divided, g divided by g to point. And actually, it doesn't matter what the action is. This is a good example of the smooth map of relative dimension 0, but it's not a type. Yes.
The map from P to M is
Yes. Yes. P to the M is smooth. It is whatever, affine bundle, line vector bundle, of course. And if you divide by these guys, it will be also smooth, because then, yes. Okay, anyway, this and
What about the other map?
is a proper. Yes, why it is proper. Okay, maybe if you don't see why it's proper, the question is you can write this one. You can write it as what is called Grothendieck-Springer resolution, G over P over G. And this is this is what is called Grothendieck-Springer resolution, or generalized Grothendieck-Springer resolution for P, and this is proper. But let me not go into it. Okay, essentially why it is true, because G mod P is projective. Yes. Anyway, this is the functor, and now what I want to say is the following. First of all, M, P, G are defined over FQ, and in particular, what is important, yes, and maybe, yes, when I say this guy, maybe there is some cheating. I really want something else. Maybe let me be more precise in the beginning to those who say, so what I really mean. So this is for every something, let us say, over FQ, and I want it FQ bar, Q bar. So anyway, so I extend scalars, and then define it over this. In particular, what is called that somehow this sheaves has the action of the Frobenius. In particular, what I claim that actually Grothendieck-Springer, it maps from sheaves M of add M Frobenius to the Frobenius equivalent sheaves or Well sheaves, where what I want Frobenius such that yes, so one, where what it is, I claim that when I write this guy is of course a collection of pairs, sheaves, and phi isomorphism between Frobenius of F and F. And let me put it isomorphism from the, just because people usually consider isomorphism, but actually morphism is enough, of course. So what I want to say is that somehow everything is Frobenius equivariant, and in particular it induces a map on Frobenius equivariant objects. And also maybe I want to say that somehow why somehow these guys are important. These guys are important. There is a Grothendieck sheaves functions correspondence, which says that actually for every f, sheaf functions correspondence, for every f in sheaves, it's give you function on FQ points on the QL bar. And let me not write, I will say somehow what is, I believe many people know what you do. You start from equivariant sheaf, you restrict to a point, then on this FQ valid point, I suppose it's falling down, no? Then somehow on this FQ5 valid point there is still action of Frobenius, and I take a trace in the derived sense. Anyway, there is this correspondence, and actually if you wish fact 2, the precise form, which says that, I believe it. What I should do?
If you can bear it.
No, I can bear it. Yeah. Okay, good. Yes, and somehow more precise form, if you wish. Okay, let me say write as a slogan and then really precise form. As a slogan, I want to say that trace of Harischandra is a trace of Frobenius on Grothendieck-Springer. G, if you wish, it's that is for every f in the sheaves Frobenius. What you can do the following thing. First of all, you can consider its. You can first take the corresponding functions. Function is what we say. It's functions on the FQ valid points. So where it lies. This guy is lies in the precisely here, right? And then you can do the following. You can take its Harischandra, or what we call trace of Harischandra. Maybe I want to say that trace of Harischandra of F. It is the same as we apply Grothendieck-Springer f and take the corresponding function. Okay? So f is what? F is lies here, right? So this guy, it's what? It lies here. And this lies also in the same thing. So this is the precise form. Somehow, what does it mean? Comes from geometry. Comes from geometry in this sense. Okay. Whew. Yes, and the proof is actually very, very easy. Proof, if you wish. It's Grothendieck-Springer. Grothendieck trace formula. No, if you wish, plus formula of the character of the induced representation. If you wish. Okay, good. Good. So this we did. Now we want actually to generalize everything to more general setting. Yes, and maybe I even skip something. So this will be the same. 2. Yes, and it will be less G-connected reductive group. And what I want that M is a twisted Levy, what it's called. That is, there are two equivalent definitions of twisted Levy. One, the definition is centralizer of S such that S in G is not necessarily torus of FQ, but not necessarily split. Or equivalently, it is that M of FQ bar into G of FQ bar. So M is of course defined, so M is defined over FQ, but over FQ bar it is a Levy. And now you want to say what kind of theory you can generalize to this setting. So if you go to generalize part 1 to this setting. Okay, so first of all, the first part was, if you remember, there was a Harish-Chandra construction, was induction. This, of course, was done by Lusztig. Or maybe, so Deligne-Lusztig did it in the case in the case of torus. The paper in general appeared by Lusztig, but some people refer it to Deligne-Lusztig. I don't know, maybe Joseph knows what is the correct attribute. Okay. Anyway, either Lusztig or Deligne-Lusztig constructed the function, let me put it Lusztig, from the MPG, where what is M? Yes. M and G is before, but P is importantly, what I want to say, that somehow P is parabolic, but parabolic is defined over FQ bar. And it will actually have some difficulties too. So choose parabolic defined over FQ bar, then you can write it Lusztig functor. Okay, first of all, there will be difference. The first difference will be before it was a functor on the abelian categories. Now there is no functor on the abelian categories. There is functor either on the K group or on the drive category. Let us say bounded drive categories of representation of M of FQ to dBg of FQ. In the case of the Harish-Chandra, I could write down your simple formula, namely this formula. Here I cannot. Instead, I can write you bimodal. What is a bimodal? Lusztig defined this. So let L, there is what is called Lang map. G minus 1 G sigma, no, sigma is for Frobenius, right? There is a Lang map, and then here you have a UP. This is, by the way, defined over the FQ bar, but okay. And then what is important, if you now say that if you now consider L minus 1 of, again, it was parabolic, in particular parabolic was fixed, it's defined over FQ bar, so its unipotent radical also defined over FQ bar. Now what's important, then this guy in G is invariant with respect to, because of this formula, what you can tell, I can tell somehow that it's invariant, it's G of FQ times M of FQ. Equivariant or invariant? Yes. We take Lang map and I take a pre-image of this. So it's a subset of Z. Let me just emphasize. Yes. Yes. It is algebraic map. It's even algebraic map defined over FQ. But because of this subset is defined over FQ bar, its preimage is only defined over FQ bar. And now it's easy to see that somehow what I claim that somehow if you multiply from the left By G of FQ it is invariant because Frobenius fixed this, and it's invariant from the right from M of FQ. Why? Because M of FQ normalizes this guy. In particular, we have a bimodal. Yes, bimodal meaning you have considered its cohomology or derived, whatever. Whatever. R gamma C, cohomology with compact support, U of P Q bar. B, it is what? Is again G of Q, M of Q. Again?
You mean U or L inverse of U?
I mean L inverse of U. Thank you. Thank you. Yes, because otherwise cohomology is not very interesting and also not very relevant. Yes. Both, yes. It will be very interesting one-dimensional vector space, but with trivial action, but it's not what we want. Yes, but this of course bimodal. And then, yes, and we define and Lusztig functions by Lusztig functor. It's by the definition is given by the same formula as before.
This is not defined over FQ, but you don't care.
Yes, I don't care because cohomology of I anyway consider. Yes, it's not defined. Right? Yes. Okay, and I consider this. So this gives you, yes, it's important. This is, of course, bimodal in a sense that somehow element in the drive category. You have this functor. And now you have ask, let us say, Lusztig, for example, conjecture or whatever how you want.
Element in the drive category of Q and vector space.
Yes, this element in the drive category of, no, actually, better element in the drive categories of G of Q, M of Q bimodals.
But still, it's semi-simple category, so the drive category is that category.
You're right. Still semi-simple category, but anyway, yes. And then of course this, if you wish, I don't know, whether I put L or not, let me not put L because everything is semi-simple. And then you have anyway functor from here to here.
What do you mean by put L? Where you want to put L?
No, yes, tensor product. Everything is derived, but because everything is semi-simple, you somehow I will not do it. Yes, let's say example. Yes, my basic example, of course, what is the basic example? If M is T, maximal torus, this is what is called Deligne-Lusztig induction, which give it for every character, for every, for Deligne-Lusztig induction for every whatever Q bar, we say that Deligne-Lusztig constructed something in the
why in the case when P is actually a parabolic which is defined over the field, we get the previous construction?
Okay, it's one exercise for. Yes, then says my best remark says that somehow if actually you even don't need this, I believe you only need if P is defined over FQ. This is the only thing you need. In particular, it's true in the Levy. Then I claim that actually this guy. What I say, I claim that Lusztig G, it is the same as Harishchandra up to some, I guess, up to some mistake. It's something like this. Why? Because if you apply Lang's theorem, okay, the idea is that somehow this is right. What is this subset? This subset is a set of G such that these guys in the UP, right? If UP is defined over FQ, of FQ, you can make it 1. And if you do it 1,
Discrete set then, yes?
what?
And then
No, it will not be discrete set. It will be discrete sets times UP, which does not have any cohomology, yes. So cohomology will be just homological shift precisely by this guy.
No.
Yes, anyway. So correct question, of course, somehow. Yes, but the answer is you would get the same thing. Okay, maybe I'm ignoring Tate twist. Let me ignore Tate twist. It doesn't.
Because the coordinates are trivial,
Anyway.
but not trivial.
Yes. Okay, good. Now there is a conjecture due to Lusztig. Lusztig meaning in the same paper. It was paper, I guess, 76. He also formulated conjecture. It is that Lusztig functor is independent of P, and also he known. I mean, actually, in some sense, in most cases, meaning first Lusztig showed for the Q sufficiently large by Lusztig, and actually this for in the case M equal T, you don't need this. But still somehow, and also if you for Q greater than 2, so this is he uses some character sheaves, meaning some rather non-trivial results in character sheaves, and for Q3 it is done by some guys. I forgot who it is, Bonafé, Michel, using computers. By computers, they showed it almost in all cases, except Q equal 2 and some groups containing parts of E6 or whatever, some anyway. This is independent of P. This function, I mean, I defined you a functor, right? This guy. And you can ask, you need P in order to define the functor. You can ask whether it's independent of P. Okay, no, at least up to character, up to simplification, let us say.
Well, what did you say? So, I mean,
Good question. Actually, it follows from our results there is a canonical isomorphism, actually. One of the things that actually we will show is that somehow there is a canonical isomorphism independent of it. Lusztig, of course, Lusztig, I believe, only calculated the characters, and somehow I believe he did it not canonically.
Computers, you mean that for exception books you need computers, or?
No, even in this, Lusztig did it only here.
But how you can use computers for?
You're asking the wrong person. Okay, good. So this is okay. So this is about part 1. What about part 2? Okay, let me give, so this was, okay, this was 1, this was whatever, something. Okay, let me say 2, maybe 3, doesn't matter. Yes, so consider now the second, let us say trace of Lusztig. It will be the same from the class function of f of q to the same thing over g, class function. And you can ask questions. Maybe question 1, does it come from geometry? And secondly, is it true that trace of the Harischandra of Lusztig, sorry?
There's a fact it's well defined, it's not obvious, yes?
What again? What do you mean well defined?
Trace of Lusztig,
No, it is. Again, everything is,
Because you have functor between the categories. So
yes, for functor, it's, it's triangulated functor, it's preserved distinguished triangle. So if you wish, consider the correspondent maps on K groups.
you say it's triangulated categories, but just everything is semi-simple.
Yes, everything is semi-simple, but yes. It's map of K groups, so it is actually very easy. Is it true that the trace of Lusztig is equal to the trace of Frobenius of the Grothendieck-Springer, for example? Yes. Questions, now answers. Question 1, the answer is yes. Okay, question 2 is after modifications.
Did you define Grothendieck-Springer in the setting? Yes.
No, yes, as was mentioned, over algebraic closed, you have the same thing.
Yeah.
But of course, you're right, you have to take a rational structure into account. You're right. Yes, and question 2, after modification.
But in order to have trace, you need weight factor.
Yes, you're right. After modification, and let me just explain you what is the problem is. Namely, what I want, as was mentioned, that somehow right-hand side somehow is not defined as it is. Maybe want to say what is the problem. Many problem is that you have a Grothendieck-Springer. We have its sheaves on M. This you can still do, because we know that the sheaves are G, but the problem is does not lift to the same guy Frobenius equivalent objects. And let me explain why and why it is connected. And actually it is, yes, and actually moreover I claim it's precisely because yes, namely, let me just explain what you're trying to get and what is the problem. The problem is as follows. Okay, yes. Okay, what you want? You start from the Frobenius of F, right? Frobenius of F maps to the F. Oh, isomorphic, but doesn't matter. And what you want? We want map from Frobenius of Grothendieck-Springer of F to Grothendieck-Springer. Let me just be yes, to Grothendieck-Springer. This is what you want, okay? But now there is a problem. Now, if you try to write this, it turns out that somehow it's very easy to see that this is Grothendieck-Springer of, this is Grothendieck-Springer of what? Of M sigma of P, Frobenius P. It's just very easy diagram chase. You can see that somehow that Frobenius applied to Grothendieck-Springer, it is, oh, sorry, it's, sorry. Frobenius of F, yes. I claim that somehow first this and this is the same as Frobenius, and after that another Grothendieck-Springer but corresponding to something else. Of course, from here, using phi, you can map to Grothendieck-Springer M sigma of P G. Again? Yes, we starting from this, right? We start from object here, Frobenius equivalent sheaf, and you want Frobenius structure. This is precisely what is mentioned, and this is not isomorphic in general. Okay, now what is the solution? Solution is as follows. We consider subcategory sheaves of G adjoint G, the same for M. Consider the category of she adjoint she character sheaves. essentially due to Lusztig. Of course, Lusztig, of course, considered mostly abelian subcategories, but it's somehow the same definition. There is a character sheaves. Then what is claimed, then what is the, yes, maybe I want to say that somehow, sorry. Maybe, you know what, let me put it here, I forgot. Yes, let us say our first theorem says, on this that actually, that this Lusztig MPG is independent of P, independent in the strongest possible sense. Namely, there is a canonical isomorphism for each two. And here, then first of all, first assertion is there is an easy lemma that if you consider Grothendieck-Springer of it preserves the category of character sheaves. If I have time, I will formulate it later, but probably I will not. So, sheaves G and G. And actually theorem 2, our theorem 2, says that actually what is important, that if you consider Grothendieck-Springer, let us say character, namely from the sheaves M, if you restrict ourselves to character sheaves, then our assertion says that actually it's independent. Namely, there is a canonical isomorphism of functors for every two. Okay, this is it. Okay, so yes, is independent. Let me put it P. Okay, and now what about the, yes, and after that, after we know this, then I claim is, okay, actually this diagram would say as corollary. Corollary says that actually the Grothendieck-Springer Grothendieck-Springer from the sheaves M of ad M to sheaves G of AG leads to Frobenius equivariant objects. Yes, sorry. Yes, there is a natural isomorphism. Actually, moreover, actually will show, yes, this is the assertion, then Frobenius equivalent object. In particular, this question is well posed, because before it was not well posed, and now, and theorem 3 says, then it is even true. What is written? Yes. Namely, yes, that meaning for every f in, let me formulate it in sheaves and add m character and Frobenius equivariant, if you consider trace of Lusztig of f, it is the same as Grothendieck-Springer of f. It makes sense. Okay, good. Now, okay, so this is good.
I have a question, maybe to basic. What are characterizations?
There is subcategory. If I have time, I will say it. If not, okay. Question time or back in Jerusalem. Yes. Okay, good. Now the question is, what we actually do. Maybe now I want to say what is the strategy of the proof. Actually, what happens that actually all the theorem, theorem 1 and 2, will be corollary of the following. So our goal is the following. Strategy of the proof is the following. 1, we want to construct functor of, if you wish, infinity two categories. No, okay, 2 is important. Infinity is, some people say that all the categories are infinity. But somehow, yes. The idea is that somehow what you will do, you construct of infinity 2 categories. Namely, I will say I am PG from it's called, so this is monodromic modules over this monoidal category. So this will be monoidal category. No, monodromic is another way of character. But here, Dennis prefers monodromic. I don't know, or character. It depends. No, the idea is that we consider Here we consider all sheaves, and you consider models of these monoidal categories, but not all models, but some models which we call monodromic or character. I don't know. Character and monodromic are somehow the same thing.
Model with respect to what monoidal structure? Convolution?
Yes, convolution. Yes. So this will be sheaves G mod. Okay, this I hope. Okay, maybe I will have at least a use. So the idea is that somehow we will actually take one categorical level higher. Okay. So remember, what was our object? Our object was what? We say O Grothendieck-Springer. So Grothendieck-Springer is what? Is functor between categories or infinity categories, doesn't matter. Right? Another one was Lusztig functors. It's also from representation to representation. So it was theorem 1 and 2 says about functors between categories. Theorem 3 says maps between vector spaces, one categorical level below. And the idea is that we can consider this and to show what is important, that it is independent of P. And why it is relevant, and then I claim that actually all the other structure follows from it.
So in particular, you prove the Lusztig conjecture without a computer?
No, let me just formulate what we show. Yes, but in some sense, our goal was to prove in somewhat, yes, and then 2, we say that, as I said, somehow categorical traces. If you consider now to show that actually trace, we can consider, for example, trace of identity. When you take the categorical, there is an operation called categorical trace. What is important, maybe I will not have time to discuss this anymore in detail, but anyway, the main property is that you reduce the categorical level by 1. In particular, if you start from the morphism functor between infinity 2 categories, after you apply trace, you have map between infinity 1 categories. And I claim if you consider trace of identity, then you get precisely Grothendieck-Springer G, this character version. Again?
Identity from where to where?
Anyway, let's there is an endomorphism. You want the endomorphism of this guy. This guy this morphism has an endomorphism called identity. There is a very nice endomorphism, but surprisingly for the categorical trace, it's very important operation. Yes. Oh, yes. And now, if you now take the trace of Frobenius of this guy, then we get precisely Lusztig map. And for there is what is called now you want what? You want to consider, yes, if you now consider the following, there is what is called trace of, you can do it twice. The idea is the trace of identity, trace of Frobenius. Okay. There is a theorem which says that somehow there is a secondary trace. Okay, so first of all, what is this guy? This guy is the same as trace of Frobenius, trace of identity. Okay, this is what is called secondary trace theorem. Meaning it commutes under some nice condition, which I of course will not say actually, but this nice condition not always satisfied. And by the way, and one of this monodromic we realized that before we saw that we could do it without this, but without monodromic it's not satisfied. So it's not completely innocent, but under some nice condition it satisfies. And now I claim that, but what is this guy? This guy, this guy, we say it is Lusztig. It's trace of identity on the Lusztig. So it is whatever. Categorical trace of identity of the functor, it's kind of easy fact. It is the same as the map of the induced map of the traces. So this is essentially equal to the trace of Lusztig map. And now you have this guy is what? Is trace of Frobenius of Grothendieck-Springer. And this is precisely theorem 3. Okay. Now I forgot. I started 25. Okay, I have another 10 minutes. Okay, let me just. I want to explain. Yes. So I will not say about categorical traces. Instead, I will explain, for example, what is kind of where the independence of P comes from, and how some condition like monodromic actually comes into play. And there it will be very important that we are somehow in the somehow two categories. We have a lot of somehow space to play in.
Can I ask a question, Paul?
Yes.
For 1, 2, and 3, you don't need monodromic, and you need only for 4, or you need it for everything?
No. Independent of P will for
Coming from 4.
again.
Okay.
Okay. If you want independent of P, it's only true. It's not true. It's somehow it's not true without monodromic independence of P.
2 and 3 are true without monodromic.
Again.
2 and 3, but then without part.
Okay, something is true. Okay, there are some assertion about two and three, and of course, somehow 2 and 3 would be easier without monodromic. But we have a stronger result here. Here we have independence of P, and without monodromic we don't. So definitely from here, from this one, it wouldn't be enough independence of P because this is dependent. Okay, good. Let me just first explain what you do without monodromic, and then at least monodromic characters, whatever. Okay, so let us say 3. Actually, I will pass to 4. Main construction. Yes, I guess I already finished this one. Okay, so we say that somehow we have a G is a group. From this follows that sheaves of G is monoidal to infinity category. Yes. In particular, okay, now consider if you know the G of UP, remember that on this action of this and M, right? In particular, what is called, if you consider sheaves on this guy, it's what is a bimodal with respect to sheaves on G, sheaves of M, bimodal category. Namely, sheaf G X convolution from the left, if you wish, this guy X on convolution from the right. And in particular, it induces functor from I M P G, I don't know, tilde, something from sheaves on M model to sheaves G model. What it is, if you have any model, I don't know, M goes to sheaves GUP, sheaves of M to M, right? The same formula as before, except it's not somehow model as usual. It's somehow one categorical level higher, but actually it is the same thing. Good. Now, why it is actually, you see them go this much better than one categorical level before. Now, for every, consider two, suppose you have two parabolics, P1 and P2. From this, I claim that there is a natural intertwining operator from sheaves of G on U P1 to sheaves G U P2. If you ask me what is the intertwining operator, the answer is, of course, what you do, you just consider G over U P1, G over U P1 intersection U P2, for projection. Not sheaves, without sheaves, right? P2, and what you do pull and push. And let me not discuss what kind of pull and push you do. It actually doesn't matter. I mean, okay, it does matter. You have to write correct formulas, but let me ignore this. Okay, and you have this one. Now, if you have a, but what's important, this is a functor of bimodals. Because, of course, these functors commute with the action of G from the left, because this is, equivariant with respect to left action here and action of M from the right. If you have functors of bimodal, this give what? This induces us this, of course, induces induces morphism between functor I am P1 G to I am P2 G. Right. Now you can ask, okay, you have a functor, whether this functor is equivalent. The answer is no. But now there is a lemma, which is essentially, it's easy lemma, says that actually if you consider its intertwining operator P1 P2 monodromic or character, I don't know what is which language better to use. If you consider sheaves G of UP1, sheaves G of UP2, let's say, let us use monodromic, and this equivalence. Maybe let me consider a particular case that actually, and general case actually follows from this particular case. What is particular case? Let us consider G is SL2, right? That in this case, what is G mod U? Is, a square minus 0. Then this intertwining operator is what is called, Radon transform. And it is well-known fact. It's actually not completely obvious, but very, very standard, and actually very straightforward, that Radon transform, it's not equivalence of categories, but it is equivalence of categories when you restrict to monodromic sheaves. And by the standard argument, actually, the general case follows from it, because as usual, so this is easy lemma. It's not completely obvious. And then I claim that this is okay, maybe, I don't have a lot of time on this, so let me just formulate you what is a character sheaves, and then I will stop from here, and then, yes, let me just explain you what is everything is about. Yes, the idea is as follows. Yeah, the idea, okay, maybe I want to say, and lemma implies that actually the intertwining operator P1 and P2 is isomorphism when restricted to sheaves M mod whatever monodromic models which were not defined. Now this is somehow answer to Joseph's question. So there is, it's not, we're not only claiming that they're abstractly isomorphic or equivalent, namely we consider the functor, which actually you have to show its property. It's property of the functor, and by the way, we cannot do it if you would do it one categorical level below. For example, if you want to consider independence here, we don't have a functor which is equivalence. But the idea is that somehow if it was independent of P before that we take trace, and of course it is independent of P after. Okay, yes, and maybe the last thing, there is a fact. Okay, maybe. Okay, so let U, G will be, U is the unipotent radical of Borel. Then there is an important fact which says that the sheaves of G models, it is the same as, if you wish, sheaves of G U models. Okay, maybe I will explain what is this guy. Maybe if I have time, I also define what is character. Let me do one categorical. Yes, the idea is that okay, what is the functor between these two guys? We know so to define the functor between models of a something, you have to give a bimodal. And if you ask me what kind of bimodal to give, and there is only essentially one option. One, it's U of P of U of P of G. U of P means sheaves, of course. Yes, and now what I claim is that it's actually
right?
what?
You're claiming Morita equivalence.
Yes, this equivalence, yes. Namely, yes, okay, Morita equivalence, you're right. It's a category of models are equivalent, it is the same as, of course, it is Morita equivalent, of course. Yes, and in particular, we want to construct a subcategory here, right? But the equivalent, in particular, if you want to construct subcategory here, it is the same as to construct subcategory here. But here, there is an action. What is important here, there is a T cross Tx on this part from the rest. In particular, there is a notion of monodromic sheaves with respect to T action. And then I claim that here there is a sheaves G, U models monodromic. Why? Because actually this means that if you wish, that the Tx via monodromic quotient. If you think somehow carefully, there is a somehow map from the monodromic, or if you wish, you can put monodromic here. Meaning somehow monodromic sheaves is of course subcategory, but it's subcategory without unit. And now it turns out that there is of course embedding, which is monoidal but does not preserve unit, and there is a right adjoint which is monoidal and preserves unit. So map from here to here is a beta functor, and in particular if you have a quotient of ring, then you have embedding of the corresponding category of models. So I defined U category here, and here is the corresponding subcategory. And character sheaves, it's something very, very similar, but let me not do it now.
You said that you use the monodromy to show that the two functor is independent of P, right?
Yes.
And then, do you need it for, you said that you also need it for 4?
Yes, I need it for this guy, yes. Yes. No, just somehow, okay. For you have some kind of this kind of Lux diagram, and you have yes, you have this, and you want that somehow all the arrows here has right adjoints, okay? And I claim that if you don't restrict to monodromic, then all these guys would have right adjoint, but this one would not have right adjoints. That's it.
So it won't be fully dualizable.
Yes, okay, or two dualizable. I don't know what we use. Maybe, okay, anyway, somehow you need that somehow enough right adjoint. This guy would not have right adjoint, but what happens that if you restrict to the monodromic sheaves, then this guy would be equivalence. Essentially, this lemma. And therefore, of course, equivalence has a right adjoint. So. by
things can't be deciphered, right?
what?
I mean, usually those places are explicit things, so like maybe there is a way to make it like elementary in the end. I don't know.
I don't know. I mean, at least I don't know. At least Peter Scholze told me that sometimes Peter Scholze wanted to show something very, very simple and very explicit thing. He defined what is ULA sheaf, and he wanted to show that they're preserved under the Verdier duality. And he said that simply failed. But with language of infinity two categories, it follows in two lines. But without it, he really failed, and he is quite a clever guy. Meaning somehow, because somehow infinity two category has some non-trivial combinatorics hidden in it. At least because somehow the assertion of Scholze was really actually okay. I'm not convinced, but I trust him that if he was not able to do it, then probably it's difficult. Yes.
So you said that the 2 in the infinity 2 is important and the infinity is less important.
No, infinity, everything is infinity.
Does it mean that in this case, again, the infinity is in fact semi-simple? Or
No, it's
so
not.
on all the lower levels, when it was like 1 infinity, the infinity was semi-simple, yes. But on this level...
No, first of all, on one level, this also, this is functor between, derived categories. It also was functor between derived categories, infinity derived categories. It's
only on the left-hand side, semi-simple. This right side...
Yes, on the basis of representations, of course, it's representation of, yes. Yes, and maybe I want to say somehow, when I say that somehow it's a map of infinity two categories, but actually there are, if you consider, when you consider trace, you need actually infinity three categories. At least as Nick Rozenblyum told me, that probably it's the first application of three categories to mathematics. Three? No, because if you consider trace, when you consider trace where?
No, there are even 4 categories appearing in the topological quantum field theory.
Okay. With topological quantum system. No, the question is whether it's mathematical or not. Let me. No, but it's a very concrete question. There is a concrete question about representation of finite groups. You would not expect that 3 categories are needed, right? Okay, I don't know.
I mean, by modules, categories over tensor categories, they form 3 categories. Objects are tensor categories.
Yes, of course. No. All the 3 categories is of course 3 categories of 2 categories or more. Yes, and monoidal categories are particular cases of these 2 categories, of course.
Yeah, so to understand tensor categories and modules of